Well, good morning and welcome to another session of e-learning. We are diving into a new module, and with that, we are looking at circles and rotation and how they are linked as well. So let's dive right on in. Travis and Tahani know how to construct the image of a rotation when given the center and angle of rotation, but today they've encountered a different issue. How do you find the center of rotation when a rotated image and its pre-image are given? They decided to explore this idea with their friends, Carlos and Clarita. Each pair of friends creates a puzzle for the other pair by sketching and drawing on graph paper which a rotation of a figure is shown, but the center of rotation is not marked. The other pair has to figure out where the center of rotation is located. Here are the puzzles they created for each other. Carlos and Clarita think that the puzzle they've been given is too easy since it only consists of a single rotated point and its pre-image. Carlos says, the center of rotation is at the midpoint, 2, 4, halfway between the image and the pre-image, and the point has been rotated 180 degrees. Clarita disagrees. The center of the rotation is at point 0, 0, since both the image and pre-image points are 5 away from the origin. I'll need to use a protractor to find the angle of rotation. Laughing, Tahani says, you're both wrong. We didn't use either 2, 4 or 0, 0 as the center of rotation when we created the puzzle. Carlos replies, I can see how both of our points can be the center of rotation, but now I think that with a single image and pre-image pair of points, any point can be the center of rotation. So this puzzle has turned out to be more challenging than Carlos and Clarita thought. List at least 3 additional points that can be considered the center of rotation and justify your choices. So as of right now, we have 3 points, correct? We have 2, 4, 0, 0, and, we have 2 points, I should say. So now what we need to do is I will go ahead and mark those 2 points. So 2, 4, and 0, 0, right? And we can see how both of them could have been used, but we need to look up some other points that could have been used for this rotation as well. So see on your own, what I want you to do first is see if you can find any other points of rotation. So go ahead and pause the video and try that. So really what we need to look for when we're looking for points of rotation is a point that is equidistant from both A and A prime. Okay, so we need to find points that are the same distance away from A as they are from A prime. So I'm going to think about maybe some slopes that would be the same, right? So if I can go over 1 and down 3, or over 1 and down 3 and over, down 1 and over 3, that might work as well. So I'm looking at this point right here. If I go over 1 from A prime and then down 3, I'm at this point right here. If I go down 1 and over 3, check that out. That must imply also that this distance between this new point and A prime is the same if their slopes are the same. Because after all, we just have made ourselves a little right triangle and another little right triangle, okay? And what we know about right triangles is that if their legs are the same, then their hypotenuse must also be the same. So that means that dotted distance here and here are equidistant. So there's another point that is true for these 2 points to have rotated about, okay? 1, 2. So if you have not found 2 other points, go ahead and do so now. All right, so what do you think now about Carlos's last statement? He states any point could be the center of rotation. Do you agree or disagree? If you agree, explain. If you disagree, what would be a better statement to make about the set of points that can be used as the center of rotation for a single rotated point and its pre-image? So we know that these lines right here are the same distance, right? As those arrows are pointing to them as well. we also have seen that 0, 0 is the same distance from A and A prime, and this point 2, 4 is the same distance from A and A prime, right? Now, if we look at those and maybe try to see a pattern, we can actually draw a line through those points that continues on. A line with the slope of 2 over 1, actually. And now, let's look at something else that's interesting about this as well. I'm going to erase these lines here just so that I have a little bit more clarity. How does that relate to the line that connects A and A prime? Well, there are a few things I know, or that I'm recognizing about it. It looks like they create a right angle, meaning they're perpendicular, right? And check out the slopes on either side. A run of 2 and a rise of -1, a run of -2 and a rise of 1. That means that these are the same, right? Which makes that line, the line of y equals 2x, that's the perpendicular bisector between A and A prime. Okay, so that line right there is actually the perpendicular bisector, which means that any point along this line will be equidistant from both A and A prime. Okay, so that means not just any point will do, but any point along this line that is the perpendicular bisector, that will be used, or that would be possible for us to be able to pick as a center of rotation. Okay? So now examine the puzzle Carlos and Clarita gave to Travis and Tahani. Find the center of rotation for this puzzle. Or if you believe there can be more than one center of rotation, describe how all of the possible centers of rotation are related. So, knowing what you do now about perpendicular bisectors, go ahead and try this one as well. All right. I'm going to go ahead and draw the line segments connecting the pre-image and the image. Okay, so I have A to A prime, B to B prime, and C to C prime. Woo. Approximately. So, we learned something interesting about perpendicular bisectors, right? We learned that for 2 points, any place on the perpendicular bisector could be used as the center of rotation. However, now we have a shape, an actual shape, right? So it can't just be any point on a perpendicular bisector. So for example, take B to B prime. If I look at the perpendicular bisector, okay, which I'm going to invert the slope essentially, and I see that the center point is right here because I could create these two little triangles right here and here. Okay, and then I'm going to take the inverse of the slope, so it will be 1/2 instead of 2, like this. Okay, so for B and B prime, the center of rotation for those 2 points alone could be anywhere on this line. But I'm not just looking for B and B prime, I'm looking for this entire figure, right? So now I'm going to look at A, and I need to, A to A prime, excuse me, and I need to find the perpendicular bisector of this line. Okay, and I see that this line has a distance of 1, 2, 3, 4, 5, 6, 7, 8. So that means that the center is going to be at 4 from one of the endpoints. So here's the center, okay? And the inverse slope right now is basically going to be an infinite slope. It's going to be a vertical line, up and down. Okay? Aha! So the rotation for A and A prime could be anywhere along this line. But if you're seeing what I'm seeing, these two lines intersect at one point so far. Now, let's see if C and C prime do the same thing. If they have a line, a perpendicular bisector, that will also land at this point, okay? So I'm going to try my darndest for the slope of C and C prime. Let's see. So I see that the slope of this, or the distance between these, is 10 and 4. It's a run of 4 and a rise of 10. Negative 10, I should say. So I know that the slope is 2, negative 5. So I'm going to do that. 1, 2... negative 1, 2, 3, 4, 5. So here's the midpoint, right? And since that's the slope, negative 2/5, I'm going to, or negative 5/2, I'm going to invert that and make it 2/5, okay? So I'm going to come the other direction now, and it's going to be positive as well, so I will go negative with both of those pieces of the slope. So negative 1, 2, 1, 2, 3, 4, 5. Would you look at that? Voila. Here is the perpendicular bisector of our next line right there. And they all intersect at this one point. So for a two-dimensional shape or a triangle that we have here, they all of their rotations intersect at a single point, which means that's the point of our center of rotation. Okay, it's 2, 1. All right. Now that we have number 3 tackled, let's figure out this next point, or this next thing. On the following page, describe and illustrate your process for finding the center of rotation of a figure consisting of several image and pre-image pairs of points. That means something that's more than just a point, right? It could be a line, or it could be a triangle, or it could be a square or a rectangle. So, if you make any claims in your description, make sure you provide a proof of your claims. Use correct mathematical vocabulary. So that means not using slang, but we're going to actually say things like the midpoint rather than just saying the middle of the line. Or we're going to say the vertex rather than saying something else to refer to it, okay? Here are some words and their definitions for terms associated with circles. Some of these terms may be useful in your written description of how to find the center of rotation. So not all of them will be useful, but they'll be useful in future tasks. So here is a list of vocabulary words for you. Now, I'm going to attach to this video a little description of how I would describe rotations. So that will be attached to this video. There are some underlined key terms as well that will be helpful for you. Those are these terms that are italicized right now. And now you can see it. Pause the video and go ahead and copy that down. Okay, the last portion here of our lecture, we are going to look at a circle where the perpendicular bisector of a chord bisects the central angle formed by the radii drawn to the endpoints of the chord. So, a lot of mathematical terms, okay, but we're going to use the previous vocabulary list to try to help us make sense of this as well. Okay, so let's go ahead and go through here. A circle, we have a circle, perpendicular bisector of a chord that bisects the central angle formed by the radii drawn from the endpoints of the chord. So let's draw ourselves a picture, okay? I always find it helpful to draw a picture when I am working on a proof. So here we go. Here's our circle. All right. And it says there is a perpendicular bisector of a chord. So here I'm going to draw a chord, and that's just a line that travels from one side of the circle, or one point on the circle, to another point on the circle. Okay, so there's a chord. All right, and I'm going to name these points as well, points A and B. All right, and now I need a perpendicular bisector to the center of this circle. So I'm going to call the center of this circle O, and I am going to draw or sketch a perpendicular bisector, okay? And then, here I should denote that's perpendicular, and it bisects those angles, or it bisects that chord. And then I have the radii drawn to the endpoints of the chord. So radii OA, or radius OA, and radius OB. All right. So they're asking us to prove this thing, that these angles, okay, I'm going to name this point M as well, that angle AOM is congruent to angle BOM, because they're saying that perpendicular bisector actually bisects that angle of AOB as well. Okay, so we're trying to prove that those two pieces, those two smaller angles, are actual halves of the fuller angle. Okay, so we're going to use some triangle congruence to help us prove this. Okay, so again, what I like to do when I'm proving something is I like to walk through my proof, kind of get a sense of where I'm going and what I know, and then I'm going to formalize it a little bit more. Okay, so I see that AM and BM are congruent, right? Because that's what the definition of a bisector is. I also know that I have two radii of a circle, and we know that radii of a circle are also always congruent. So that's it for this portion of the lecture. Go ahead and tune in to our Google Meet, and we are going to prove this following theorem on our Google Meet. Okay? I look forward to seeing you all there.